Hi, this is Jason Armstrong, and I'll be giving a presentation on our project. As you can see by the graphic, we built something, but not out of Legos, unfortunately, but instead a computer compiler. We will begin with the technical aspects of the project, specifically the design pattern we used, some design trade-offs, something that was unique to our project, and finally, what some of the future work on the compiler would be helpful to do. Here are the design patterns we used, specifically the builder and observer design patterns. The builder pattern was used in the generation of Step 3, the symbol table, and Step 4, the code generation components of the compiler. Both used classes from the little base listener generated by Antler. This design allowed the program to share the same resources while maintaining its own functionality for each step. Also in Step 3, we needed to choose between the listener design pattern, which was built into Antler, or use the visitor design pattern, which would have required explicit visit calls to accomplish the task. We chose to use the listener, and the various listener files use this observer design pattern. For the design trade-offs, first we used an array list in Step 3, then in Step 4 we used an array list to store expressions, and a hash map to store registers. As we said earlier, we opted for the observer pattern when we used the listeners for Step 3 as a means for taking the easy road, since Antler already had these in place. If we were to use the visitor design pattern instead, then we would have needed to code them to visit areas we needed explicitly, which seemed like a lot of extra work, comparatively speaking. For Step 4, we opted for the full approach of creating the abstract syntax trees, using an intermediate representation of the 3 address code, and then converting that into the rather final state of the assembly language. The reasoning for this was that debugging it would be difficult if we couldn't see the changes as they occurred. Furthermore, we opted to skip the optimization step in Step 4. While this would be important for a commercial level programming language, it wasn't needed for credit, honestly. Another design trade-offs that we encountered were the numerous items to set up at the beginning, such as version control and communication methods. Unfortunately, reality as well as the COVID-19 set in, and things changed radically. Work and school now began to happen at home instead of on campus and at work. For our unique aspect, our code was able to run faster by producing a smaller amount of clock cycles, which we worked really hard to decrease, allowing the compiler to ultimately run faster. For the future work, we will optimize our compiler in the following ways. Currently, we have few code optimizations and no runtime memory management in our compiler. We would like to review our grammar to see if there's any rules that can be modified to improve the efficiency of our parser. We would also like to implement optimizations to use fewer registers in the tiny code to save on memory. Maintaining the version of the compiler is a sure thing that we will focus on. Also, we would like to further explore the version control software, GitHub, for which we lack knowledge and training, which would have been beneficial for the project. Here we will talk about the development aspects of the project, namely how the team worked together and the software development lifecycle. For a broad overview of our team, we started with the 2 team members, number 1 and number 2, and increased to 3 after Step 1. Therefore, we show 200% for Steps 0 and 1, since member number 3 was working on the project solo prior to joining us. Gaining member number 3 worked out incredibly well, since one of the original team members, member number 2, became unavailable once COVID-19 outbreak began. When this happened, working and studying from home became the norm, along with social distancing. Team member number 3 was exemplary in the coding portion, while team member number 2 focused on the reports. And here are the specific members of our team. For the software development lifecycle model, the waterfall model fits fairly close to the way the compiler was written, since it was very linear in its steps from requirements to design, then implementation and testing. However, there were also hints of the iterative software development lifecycle model. The iterative route would have occurred when the code changed hands from one programmer to another, since they had to effectively start the process from the beginning to be able to pick up effectively where the previous coder left off. Also, each step used these waterfall steps, which makes the iterative model even more appropriate. And thank you for watching our presentation.